All right, so I think we were on page 21, is that right? We finished off with the other examples? Okay, so we're going to continue with Euler's method. Basically the ones that we're going to look at are giving us information in different formats, like tables instead of just explicitly telling us particular points. So the process doesn't change. We're still going to use those iterations, okay, those steps over and over and over again. We just got to make sure that we can identify the information that's needed in order for us to do that, okay? So let's go ahead and take a look at this first one for number 3. Assume that f and f prime have the values in the table. Use Euler's method with 2 equal steps to approximate 2.6. So we're essentially trying to figure out what's the y value in this last block. If we were to plug in 2.6 into the function, what would we get out? But Euler's method involves a process. You have to use previous points to figure out new points. So in order for us to figure out what 2.6 is, we have to first figure out probably 2.8. Okay? So can we identify, perhaps in this table, what our beginning x value is, what the beginning y value is, and what our step should be? Yeah, oh, go ahead, do it. Okay, so if you were to take the x value of 3 and plug it into the function of f of x, you would get 2. Okay? Remember, f prime means derivative or slope. That's not representing a point. That's representing a tangent slope. Okay? So beginning x, beginning y. What about our step? If we want 2 equal steps to go from 3 to 2.6, maybe you can use the table to kind of help you out what the step is?
Please excuse interruption. We need any remaining freshmen who have not had their picture taken, please report to the auditorium.
Yeah.
That is any remaining freshmen. If you do not get your picture taken, Mrs. Hoff is going to call you out individually. Have a great day.
What a threat. What a threat, you know? All right, so we're starting at 3. Notice how we want to go to 2.6, so we're going kind of backwards on a number line, so our step would have to be negative. Okay, so let's go ahead and maybe we'll set up our table. You don't have to do this if you don't want to. It just helps me to keep everything organized. If we're doing 2 equal steps, we're going to need 2 more x and y coordinate values besides the 3 and the 2 that we started with. All right, so question is, how do we use the step to help us figure out the next x values? We start at 3, yeah.
You just add the step, and in this case we subtract the
Right. Yep, you just add the step. Add negative 0.2, so you'd be subtracting. So the x's are always the easiest to fill out. How do we use the step, though, to help us figure out the new y values? This is where it's a little different. Do we remember Euler's method from yesterday, what we did? Let's see. What do you think, Eric? Yeah.
We take the previous y value
Okay.
and subtract the step multiplied by the slope at that point.
Okay. So we take the previous y value plus the step, but in this case we would be subtracting, times the slope from the previous point. Now we don't have any equation to work with like we did yesterday, so we're going to have to use the table to help us out. So in terms of the slope from the previous point, we'd be looking at our derivative row. And if we want the slope at the previous point, notice how the previous x value was 3. So the slope from the previous x value was 0.4. All right, so doing a little calculation, we have 2 minus 0.08, right? So 1.92. So if you wanted to, on your table, you could do 1.92 in that little block. Remember, this is just an approximation. It's not the actual point, but that's all we really have to go off of using Euler's method. So now let's try to find our last y value. We need to take the previous y value, 1.92, plus the step times the slope from the previous point. Do we know that based off the table? Yeah.
0.7.
The 0.7, right. All right, so 1.92 minus 0.14. $1.78. All right, so there's our approximation. We could say f of 2.6 is approximately, little squiggles, 1.78. You doing okay? All right, let's check out the next one. Kind of another table format. The table to the left gives selected values for the derivative of a function on an interval. If g of -1 is -2, use Euler's method with a step size. They're being so nice to us, to approximate g of 2. So it looks like we know the beginning x and beginning y based off that point value. And they're even telling us the step. Let's see, if we add the step once to our current x value, we would get 1/2. And if we add the step again, we would get 2. And it looks like we can stop there because we're trying to approximate g with an x value of 2. Let's see, go ahead and try to find your next y values to eventually get your approximation. This is also a multiple choice type question, so eventually you should be anticipating one of A, B, C, or D, or E to be the solution. All right, so let's check this out. We have previous y value plus the step times the slope.
Okay, this is the last call for anybody who has not had their picture taken. That is, anybody who has not had their picture taken needs to report to the auditorium. Have a great day.
All right, previous y value plus step times slope from the previous point. So we're going to have to use a table to help us out. Notice how the previous point has an x value of -1, so that would give us a slope of 2. Solving from there, we can get 1. So if we repeat the process, previous y value plus slope times the slope from the previous point. The previous point had a y value of 1/2, so that slope would be 1. All the other information in that table is kind of I don't want to say pointless, but not necessary for this problem. They're trying to trick you, make you use a different number, so eventually we'd get 2.5. It worked. Sometimes it does. All right, so on the back, we're going to do a Euler's method on steroids. We ready? Maybe? Okay, so I'm going to see if I can show you guys on a calculator how to do this fairly quick, not necessarily quickly, but make it easier for you. We're going to use Euler's method to approximate the first 10 solutions, like the first 10 points to this particular differential equation that passes through the point 0, 1. So that's our beginning x and beginning y, and with a step of 0.1. Okay, so if we start with 0 and we add the step, we'd have 0.1 as the next point, 0.2 as the next one, and I think you guys get the hint for all of the next x values. Okay, so to figure out the next y, we need the previous y value, which is 1, plus the step, times the slope at the previous point. Now there's no table to go off of for the slope in this one. We actually have an equation. So to find the slope at the previous point, we're going to have to plug in the previous x value and subtract the previous y value. So that would look like 0 minus 1. So all that together would give us 0.9. Right? Okay. If we try the next y value, we need the previous y plus the slope, or sorry, plus the step, times the slope from the previous point. Your previous point is the x value minus the y value. And looks like we would get 0.82. Okay, so in terms of your calculator, I'm hoping that this can show up nicely. If we were to type in this first y value that we calculated, 1 plus 0.1 times 0 minus 1, okay, hit enter, you get that 0.9 we found. Are we familiar with how we can bring up a previous entry? Do you know how to do that? Okay, so you have to hit second and then the enter button, and it'll bring up what you previously typed in. Notice how the next y value we want to find has a very similar setup. We just got to change the 1 to a 0.9. Okay, so we'll go there. And to change the 1 to a 0.9, we're going to use the insert command. You see how it's blue though above the delete button? So you have to do second insert. And you can go ahead and type in 0.9 instead of the 1. You see how I can change it? Okay. And then I also need to change 0.1 minus 0.9. So you can just go ahead and type that in if you want to. And you get the 8.2. Okay. If I anticipate the next one, I can hit that second entry again. I'm going to have to change the 0.9 to a 0.82. So I'll hit that insert and do 2. Make sure you delete the 9 though, because we don't need that anymore. And then I gotta change the 0.1 and the 0.9, bless you, to a 0.2 minus a 0.82. So there's our next one. So if you want to use that capability of your calculator, you can, instead of having to write all them out. Maybe some of you prefer that, yeah.
It's easier if you just put the answer in place of the numbers, and then you can just put entry.
So there's okay, so what are you saying there if I hit,
So instead of putting .82,
yeah?
put your answer. So that you
Oh, because it's going to keep, okay, so if I do
just keep pressing
entry and then enter,
And then change the .82 to answer, and both .82 to answer. So second.
but you'd have to change that one as well, right? Eventually?
Oh, yeah.
Okay,
That's
so,
easy.
okay, so answer, and then this one would be 0.3, and then answer, delete, delete. Is that what you're saying? You could do that, yep. So then, oh, and now that you have the answer stored in there, you can do entry, and then change that to 0.4. There's your answer. Can we not see it? Okay. Here, maybe I'll zoom out. Okay, so what just okay. Let's go ahead and start from the beginning. So we had 1 plus 0.1, 0 minus 1. Okay, that was our first y value that we calculated. You can go ahead and hit enter. There's an answer command that's blue. It's right by the negative button. You see how it says ANS? Okay, so if you hit second and then negative, that answer ANS will pop up on your calculator. So what it's doing is it's taking your previous answer, which is in this case 0.9, and it's substituting it in on your calculator in that spot. So if we type in answer plus 0.1 times, this would be the previous x value, because now we're finding the next y value. So we have answer plus 0.1 times previous x value, and notice how we need the previous y value also. So we could use another answer in that case. So this is essentially 0.9 plus 0.1 times 0.1 minus 0.9, because 0.9 was the previous answer, and we'll get the 0.82. So now, if you hit the second entry again, you see how the answers still pop up? This time, the previous answer was 0.8, right? So we would have 0.8 plus 0.1. What you have to be aware of is that you have to change this 0.1 though to 0.2, because that was the previous x value minus that 0.8. And there's the 0.758 that we got before. So if you keep hitting second entry and then just making sure you change that one value, you can get all of the other solutions. I'm not saying this is going to be the setup every time. This is just how it happens to work out for this particular differential. Okay, it all depends on the equation you have. So if you like that, we can keep going through our calculator and filling in the approximation points on the table. Do you guys think you can fill those in using that? Is it checking out? We got those numbers? Yeah? Okay. Nice, nice, nice. Okay, so for what we did here, just as kind of an FYI, not necessarily an exploration, but I hope we realize that this differential equation right here is not one that we would be able to solve by hand. Okay, we can't really separate the variables and integrate. Okay, that's how we normally find our exact solution. Okay, we separate variables and integrate, but we can't do that for this one. This is something you would probably discuss in that differential equations course I think I mentioned yesterday. Okay, but this one we would not be able to do. So what Euler's method does is it gives us a way to figure out what the solution curve might look like. So if you take a look at the graph at the bottom, the exact solution curve is that lighter line. And if you were to plot all those points that you just found in that table, you would actually create the darker line. So do you see how close your approximation is to the actual one? Even though you might not be able to find the function by hand, you at least have a table of values that's close enough to that function to probably use as some estimation values. Okay, so Euler's method is very, very good at approximating solution curves. Let's say you did take that differential equations course and you did solve this one by hand, you would actually end up with this solution. Okay, so this is the equation of that light line of the graph on the bottom. I just want to confirm that this is the equation based off of that differential equation that we started with. So if you were to take the derivative of this equation, can we do that real quick? Can we practice our derivative rules? If we did y prime, we'd have y, not y, 1 minus 2e to the negative x. Okay. So notice how if we take the derivative of this equation, it doesn't exactly look like the derivative they gave us at the top, right? Okay, because this is telling us y prime is x minus y, but what we found was y prime is 1 minus 2e to the negative x. Okay, they don't look exactly the same, but that doesn't mean they're not equal. Okay, what if we try to manipulate this one to make it look like that? Okay, so we know y prime is x minus y. Can we substitute anything in to either of those x or y variables? Do we know what x is? Do we know what y is? See, isn't y this equation right here? Okay, so let's check this out. If we were to take x minus this equation that you could probably find in that differential course, and we started to subtract, or not subtract, but distribute in that subtraction, notice how the x's would cancel out, right? And then we would have a plus 1, and then a minus 2e to the negative x. And now, don't they match? Right? Okay. So there is a way for us, even though we can't figure out this one by hand, we could at least confirm that this is the solution to this differential equation. Okay, because eventually if we check their derivatives, they match. Okay, so in terms of the graph at the bottom, to find the exact solution curve, at least with what we're familiar with, we'd have to separate variables and integrate. But if we're going to approximate a curve, that's when we're using this Euler's method for differential equations that we necessarily can't separate and integrate, at least not at this level. Okay? We're going to check out 2 free response type questions tomorrow that kind of involve this Euler's method idea. But maybe if you want to try some homework problems tonight and bring in some questions tomorrow, if you have any, we can look at some of those. Okay? Just make sure I have your homework before the bell rings or by the end of the period. Okay?